The number of conductors does not impact the motor's amperage draw. Amperage is determined by power in watts and voltage. In a given scenario, the motor draws 53.8 amps. This remains constant irrespective of using one or two conductors for wiring. The National Electrical Code, or NEC, mandates breaker sizing based on the motor's amperage draw. In this instance, it's 53.8 amps. Similarly, the NEC specifies conductor sizing according to the motor's amperage draw, which is 53.8 amps. Therefore, a 60 amp breaker and number 6 copper THHN conductors are required. Let's delve deeper into motor amperage calculations. Firstly, you need to determine the motor's full load amperage or FLA. This can be found on the motor's nameplate or in NEC tables such as Table 430.250 for 3-phase alternating current motors. These tables provide the FLA for various horsepower ratings and voltages. Secondly, once you have the FLA, you need to apply appropriate adjustment and correction factors. These factors account for conditions like ambient temperature and the number of current-carrying conductors in a raceway. NEC Section 310.15 provides guidance on these factors. For example, if the ambient temperature is higher than 30 degrees Celsius, you may need to apply a correction factor to the conductor's ampacity. Thirdly, determine the minimum conductor size. NEC Section 430.22 specifies the minimum conductor ampacity for motor circuits. Generally, the conductors must have an ampacity of at least 125% of the motor's full load current. This ensures that the conductors can handle the continuous load of the motor without overheating. Fourthly, select the appropriate overcurrent protection. NEC Section 430.52 provides guidelines for selecting the correct overcurrent protection device, such as a circuit breaker or fuses. The overcurrent protection should protect the motor and conductors from overloads and short circuits. The maximum size of the overcurrent protection device depends on the type of motor and the type of overcurrent protection used. Fifthly, consider voltage drop. Voltage drop is the reduction in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause motors to overheat and perform poorly. NEC Section 210.19, Informational Note 4, recommends limiting voltage drop to no more than 5% for the feeder and branch circuit combined. To minimize voltage drop, use larger conductors or shorten the length of the circuit. Sixthly, grounding is essential for safety. NEC Article 250 provides requirements for grounding electrical systems. The motor must be properly grounded to provide a low impedance path for fault current to return to the source. This helps to protect personnel from electric shock and prevents damage to equipment. Seventhly, consider the type of enclosure. The enclosure protects the motor from the environment and prevents accidental contact with live parts. The type of enclosure required depends on the location and application of the motor. For example, motors installed in wet or dusty locations require a watertight or dust-tight enclosure. Eighthly, use the correct wiring methods. NEC Chapter 3 provides requirements for wiring methods such as conduit, cable, and raceways. The wiring method must be suitable for the environment and the type of installation. For example, in corrosive environments, corrosion-resistant conduit and fitting should be used. Ninthly, properly terminate conductors. Terminations must be made with approved connectors and methods. Loose or corroded connections can cause overheating and voltage drop. Tenthly, label all components. Labeling helps to identify the components and makes it easier to troubleshoot problems. Labels should be durable and legible. When dealing with motors operating at 208 volts, it's important to understand the characteristics of this voltage level. 208 volts is a common voltage in three-phase power systems. It is derived from a 120 volt single-phase system. In a three-phase 208 volt system, the voltage between any two phases is 208 volts, and the voltage from each phase to neutral is 120 volts. The 208 volt system is often used in commercial and industrial buildings to power motors and other equipment. When selecting conductors for a 208 volts motor, you must consider the voltage rating of the conductors. The conductors must be rated for at least 208 volts. THHN wire is a common type of conductor used in electrical wiring. THHN stands for thermoplastic high heat nylon. THHN wire is insulated with a thermoplastic material that is resistant to heat and moisture. It is also covered with a nylon jacket that provides additional protection. THHN wire is commonly used in conduit and raceways. It is available in a variety of sizes and colors. When selecting THHN wire, you must consider the ampacity of the wire. The ampacity is the maximum amount of current that the wire can safely carry. The ampacity of THHN wire depends on the size of the wire and the temperature rating of the insulation. NEC Table 310.16 provides ampacity ratings for THHN wire. When selecting a circuit breaker for a 208 volts motor, you must consider the interrupting rating of the breaker. The interrupting rating is the maximum amount of fault current that the breaker can safely interrupt. The interrupting rating of the breaker must be greater than the available fault current at the point of installation. The available fault current can be calculated using a short circuit study. When installing a 208 volts motor, you must follow all applicable electrical codes and standards. This includes the NEC and any local codes. It is important to hire a qualified electrician to install the motor and ensure that it is properly grounded and protected. In summary, calculating motor amperage and selecting the correct conductors and overcurrent protection is critical for safe and reliable operation. Always refer to the NEC and consult with a qualified electrician if you have any questions or concerns. Now, let's address some common misconceptions about motor wiring. One common misconception is that using two conductors in parallel will reduce the amperage draw of the motor. This is not true. The amperage draw of the motor is determined by the power and voltage, not the number of conductors. Using two conductors in parallel will reduce the voltage drop in the circuit, but it will not change the amperage draw. Another misconception is that you can use a smaller breaker if you use two conductors in parallel. This is also not true. The breaker must be sized to protect the motor and conductors from overloads and short circuits. The size of the breaker is determined by the motor's full load amperage, not the number of conductors. Another misconception is that you can use a smaller conductor if you use two conductors in parallel. This is also not true. The conductors must be sized to carry the motor's full load amperage. The size of the conductors is determined by the motor's full load amperage, not the number of conductors. Using two conductors in parallel can be beneficial in certain situations. For example, it can reduce voltage drop and increase the ampacity of the circuit. However, it is important to follow all applicable codes and standards when using conductors in parallel. NEC Section 310.10 provides requirements for conductors in parallel. When using conductors in parallel, the conductors must be the same size, material, and insulation type. They must also be terminated in the same manner. The overcurrent protection device must be sized to protect the smallest conductor in the parallel set. In the specific case mentioned earlier, a 15 horsepower 208 volts 3-phase motor will draw approximately 53.8 amps according to NEC tables. Therefore, the conductors must be sized to carry at least 53.8 amps, and the overcurrent protection device must be sized to protect the motor and conductors from overloads and short circuits. A 60 amp breaker and number 6 copper THHN conductors are appropriate for this application, provided that all other applicable codes and standards are followed. Remember, safety is always the top priority when working with electricity. If you are not qualified to perform electrical work, it is important to hire a qualified electrician. Always disconnect power before working on any electrical equipment. Wear appropriate personal protective equipment, such as safety glasses and gloves. Follow all applicable codes and standards. Take your time and be careful. Electricity can be dangerous, but it can also be used safely if you follow the proper precautions. Let's consider additional factors related to motor installations. Firstly, understand the motor's service factor. The service factor is a multiplier that indicates the motor's ability to handle occasional overloads. A motor with a service factor of 1.15 can handle 115% of its rated horsepower for short periods. Secondly, consider the motor's starting current. Motors draw a much higher current when they start than when they are running at full speed. This is known as the inrush current or lot rotor current. The inrush current can be several times the motor's full load current. Thirdly, protect against single phasing. Single phasing occurs when one phase of a three-phase power system is lost. Single phasing can cause motors to overheat and fail. Fourthly, use proper motor starters. Motor starters are used to control the starting and stopping of motors. They also provide overload protection. Fifthly, implement preventative maintenance. Regular maintenance can help to prevent motor failures. Maintenance tasks include lubricating bearings, checking connections, and cleaning the motor. Sixthly, choose energy-efficient motors. Energy-efficient motors can save you money on your electricity bill. They also help to reduce your carbon footprint. Seventhly, consider harmonic distortion. Harmonic distortion can cause problems with electrical equipment. Eighthly, properly size the motor for the load. An undersized motor will overheat and fail. An oversized motor will be less efficient and more expensive. Ninthly, consider the altitude. The altitude can affect the motor's performance. Motors are typically derated for high altitude applications. Tenthly, follow the manufacturer's instructions. The manufacturer's instructions provide important information about the installation, operation, and maintenance of the motor. When troubleshooting motor problems, start by checking the basics. Check the power supply, connections, and overcurrent protection device. If the motor is not running, check to see if it is tripped out on overload. If the motor is running, but is not performing properly, check the voltage and current. Also, check for any signs of overheating or vibration. If you are unable to troubleshoot the problem yourself, contact a qualified electrician. Remember, working with electricity can be dangerous. Always take the necessary precautions to protect yourself from electric shock.